Welcome to Study Loop.
Welcome to a new problem. This time we're given a block that's on a sliding surface. It's sitting at rest on a sliding surface. That means that the initial velocity of the block is 0 meters per second. So it's not moving. That's what we're given. And then also we're told that the coefficient of kinetic friction for this surface is 0.2. Another piece of information that we're given is the mass of the block, which happens to be 1.20 kilograms. We're also given a bullet, so there is a bullet that's fired. So this is kind of like the before, what happens before. So a bullet, uh, the mass of the bullet, we're going to call it L, is given as 5 grams. And we can change that 5 grams right away to kilograms by saying this is multiplied by 1 kilogram of a thousand grams, and that gives us 5 times 10 to the negative 3 kilograms. That's the mass of the bullet. The bullet is moving with an initial velocity that happens to be the bullet has an initial velocity. We still don't know what that is, and that's what we want to find out. What's the initial speed of the bullet? That's our goal. Okay, given all this information, the second aspect of the problem is once the bullet hits the block and sits inside of it, the block starts to move in the right direction. And so the outcome of this movement is a distance travel equivalent to, so we're going to call that S equals to 0.310 meters. That's the distance traveled. It's going to come to a stop. So the block is going to stop at some point. Okay, the block is going to stop at some point. And that's the distance covered. There's almost some, I would say, some resistance from friction. So there's a frictional force pointing in the opposite direction of the motion, F of F. And we can always compute that friction. Okay, we can compute that frictional force. So two ideas we're going to use. We're going to use the law of conservation of momentum. And also we're going to use the computations for frictional force. So that's the first thing we want to compute. What's the frictional force between the block and the surface? Remember, the force of friction happens to be, we need the frictional force because it's going to help us determine the work done by friction. Okay, so we need that. We have the frictional force is mu times the normal force. Remember, when this thing is moving, there's a normal force pointing that way, and then there's a weight, the weight of the block. Now here it's going to be the weight of the block and the bullet. So we have the mass of the block plus the mass of the bullet together. Okay, so the first thing we want to do is obviously compute that frictional force. So this becomes F of F equals to mu times the mass. This is kind of like the combined mass of the block and the bullet times the acceleration due to gravity. And so that's the information we're given. And then on top of that, we want to find the work done by friction, and that's just the frictional force times the displacement, this S displacement right here. And so the work done by friction is mu times mb plus ml g times S. That's the work done by friction. The second part of the problem, we have to so our goal is to find the initial velocity of the bullet. A law of conservation of energy. So here we're using law of conservation of energy, and we're saying that the so we're using two laws. First of all, law of conservation of momentum. Okay, we're using law of conservation of momentum, and then also the work energy theorem. So let's kind of like clarify that. We want to know what's so there are two components here. So we have the work done by friction. It's going to be equivalent to the change in kinetic energy of the system, which is the work done by the bullet and the block. So it's kind of like that. We already have work done by friction, mu so here we'll write work done by friction is equal to work done by the bullet plus the block, and work done by friction from this side is mu mbml, or mb plus ml, so mass of bullet and mass of block, gs. And then we want to find the change in kinetic energy of the system. So that's 1/2 mv squared, where we're involving the mass of the bullet plus the mass of the block. 1/2 mv squared, and then times the velocity, which is the final velocity of the system. Remember, if you go back, you see that the system, it's going to be moving this way with the final velocity. Okay, it's going to be moving towards the right with the final velocity. So we have the initial velocity of the bullet, and then the final velocity of the bullet and the block. So this is the final velocity of the block and the bullet. Coming back, this is the final velocity of the block and the bullet, and we square that. Okay, we square that problem. So then our goal is to find that final velocity, because it's going to help us solve certain the initial velocity of the bullet. So final velocity of the block and the bullet becomes, notice we can divide both sides by that. This is always the advantage of using variables up until the end, because something special can happen like that. And so you're left with a simplified problem. We can multiply both sides by 2. And so, we have 2 mu g s, 2 mu g s. This is squared. Okay, that's what we have right there. And then that can help us get the final velocity of the block and the bullet, which is just the square root of 2 mu gs in that problem. If you plug in the numbers, you can get an actual value in that case, in simplifying that problem. So mu 0.2 times 9.8, so this is the square root of 0.2 times 9.8 times 0.2 times 9.8 times the displacement, which is 0.3 0.10. That's what it is. Let's just check if we got our steps right. So our displacement is 0.310. Did we miss out on something? I don't think so. Got 0.2. Oh, yeah, we have the mass of the bullet and the mass of the block. So 0.2, those two combined, and 9.8. That's the frictional force. Yes, so we're going to come back and you can see we're doing the connection, the work done by friction, which is mu mb ml gs. We have that right here, mu mb ml gs. And then we also have the kinetic energy of the system. That's the change in kinetic energy minus the initial kinetic energy of the system. Remember, the initial kinetic energy of the system only involves the bullet so the initial kinetic energy of the system is 0 meters, is 0, because the bullet the bulletin block, the initial velocity of the block is 0. So, you know, the wooden block is at rest. Okay, so the wooden block is at rest, so we can always ignore that. We can always ignore the initial velocity, and then, you know, plugging in these numbers, we bring the 2 up, so we have 2 mu gs. Okay, we have 2 mu gs, and then the final mass. We have the final mass, so 1/2 m final squared. You know, just to check that our numbers are right, this is 2 mu gs. Yes, so let's just confirm that this is okay. The masses disappeared. Okay, the masses disappeared. So we got square root of 2 times mu times 9.8 times s, which is 0.310, and that should give us, very good, yeah, we're on the right track. So, you know, this is our final velocity. You know, you can compute it just to test final velocity for the bullet and the block, and that's fine. But the best way is just to keep the variables up until the end. So we're going to now go to use the law of conservation of momentum. So using the law of conservation of momentum, we just say the initial momentum of the system equals the final momentum of the system. So we want to think about the initial momentum of the system, and that's the mass of the bullet times the initial velocity of the bullet plus the mass of the block times the initial velocity of the block equals to the mass of the block plus the bullet times a common final velocity of the block and the bullet. Remember, we already have this from this part of the problem. So we come back and plug in numbers. We do know that the initial velocity of the block is 0. This one is 0 because it's at rest. So this is going to be 0. and our target is to find the initial velocity of the bullet. So we're saying mass of the bullet, initial velocity of the bullet equals to mass of block plus mass of bullet times the velocity of the block and the bullet. This is our target, so we divide both sides by the mass of the bullet. And now we can comfortably plug in numbers. We have mass of the bullet, which is we computed to be 0. Or rather, we could we could write it in terms of scientific figures because of the way the numbers are. So we have 5 times 10 to the negative 3 kilograms. That's the mass of the bullet, plus the mass of the block, which is 1.2 kilograms. Actually, we should switch positions because the left side is the block and the right side is the bullet, just to make sure you're comfortable with the process. So 1.2 kilograms and then plus 5 times 10 to the negative 3 kilograms, like that. All of this has to be multiplied by this velocity, which when we go back, we find it's 1.10 meters per second. And all that's divided by the mass of the bullet, which is 5 times 10 to the negative 3 kilograms. So you plug in the numbers, and we can comfortably say that the initial velocity of the bullet happens to be 265.1 meters per second. Okay, so that's how you run that problem. We're given a problem, a bullet and a block. We have an initial scenario, and then we have a final scenario. We use the law of law of conservation of energy at some point, and then we also use the law of conservation of momentum at some point. But we have to get the frictional force, because that's the one that's going to help us to deal with the law of conservation of energy. And the frictional force is the coefficient of kinetic friction, which we call mu k, times the normal force. But this is the normal force involving both the mass of the bullet and the block. We compute that, the work done by friction, and then we compare the work done by friction to the work done by the bullet and the block. We simplify. Always a good habit to keep the variables up until the end. See how it simplifies to a simple problem, a simple expression. That's the final velocity of the bullet and the block. It's radical 2 mu gs. And then you go back and use the law of conservation of momentum, because your goal is to find the final velocity of the bullet. So you reorganize the problem. On one side, you have the initial momentum, and then on the other side, you have the final momentum. You solve for the final velocity of the block, of the bullet, using algebra. Hope you enjoy the problem. Thanks for watching it, and see you next time. And if you have any questions, feel free to send them my way. Okay, thanks. Bye.